Welcome to our expo! Over the past few months, we have been researching electromagnetism. So, we decided to build a motor that was powered electromagnetically.
Hey, what is electromagnetism?
Good question, Shiraz. Electromagnetism is the branch of physics dealing with electric fields, magnetic fields, and the interaction between them.
What is a field?
In the case of gravity, mass is alerting the space around it, which is called a field. A different mass is reacting to it, either by being pushed or pulled. This same experience is done by charges and magnets.
In physics, we call this push or pull a force, so a field is a force. What are the kinds of fields?
We are going to be discussing magnetic fields and electric fields.
What is an electric field?
An electric field is a region of space around an electrically charged particle or object in which an electric charge would feel force.
Here, we see electric field lines originating in the positive end and terminating in the negative end. And we also see that like charges repel and unlike charges attract. In these photos, how the field line forces act with different sets of charges. A magnetic field is a field of force. A common example of a field of force is gravity! Earth is creating a gravity field of force around it, and any mass above Earth, for example, us, is reacting to this field by force by being pulled by it down. Similarly, once a magnetic field exists in some area of space, other magnets placed in the area of space will react to this field by either being attracted or repelled.
A magnet creates a magnetic field around itself that other magnets react to. Once a magnetic field exists, if you place a magnet in it, it will orient itself in such a way that the magnet's north pole is in the direction of the magnetic field lines.
So, since the magnetic field lines are directed from the North Pole to the South Pole, that means that the North Pole of the new magnet will point in the direction of the South Pole of the first magnet, which created the magnetic field. So what happens if two like poles are facing each other?
Then they repel. For example, if these are south poles, the field lines on the source magnet will be directed into it, and therefore the south pole of the second magnet cannot be attracted in this direction, because this is what the North Pole should do. And the effect is the reverse of attraction, which the reverse is repulsion.
Wait, so let me get this straight. Electrical charges in motion create a magnetic field, just like regular magnets?
Yes, it's crazy. But the main difference between electromagnets and regular magnets is that an electromagnet is a closed and open circuit, while regular magnets only create a closed circuit. There is a constant magnetic field.
Are there other uses for this phenomenon other than the electromagnet?
Yes. One of the discoveries is a generator. It was discovered that electric current can be generated by changes in a magnetic field.
So how do generators work?
Generators transform mechanical energy into electrical energy.
Another use of electromagnets is called a motor. A motor is used to convert electrical energy into mechanical energy.
Now, a break in our regular scheduled program to explain the right-hand rule.
The right-hand rule that we learned about had to do with determining vectors, but there is another version of the right-hand rule within electromagnetism.
A current carrying wire placed in an external magnetic field is experiencing a force acting on it, and this right-hand rule is a simple way to determine the direction of the force.
The magnitude of the force is dependent on the following factors. I equals current, always travels positive to negative.
B equals the direction of the magnetic field, always travels north to south. F equals the force of the magnetic field, dependent on I, B, and B. If B and I are not perpendicular as shown, the force will also be dependent on the angle between them.
This is our setup where north and south is our magnet, and the I, the plus minus, is the current carrying wire. So we know that I always travels from plus to minus, and B, the direction of the magnetic field, always travels from north to south. So we can use the right-hand rule to figure out the direction of the force of the magnetic field. So since I is going from right to left, like this, and our B is going down from north to south, which is this way, our force is going outward, out of the page. Let's switch things up, and instead of having the current going from right to left, we switch the signs and have the current going from left to right, plus to minus. So we can see that the right-hand rule still applies here. So we know that the current is I is going this way, B is still going this way, and our force is going inward, as you can see here.
How exactly do motors work?
A motor works by making a loop out of electric wire with a current flowing through it and putting it in a magnetic field, for example, between two magnets. A magnetic field exerts a force on a current carrying wire placed in it. And when this contraption is designed properly, this force is translated into a torque that subsequently translates to continuous rotational motion of the frame.
This rotational motion can be used as is. For example, if the motor is driving a ceiling fan or a wheel, or converted into linear motion, for example, an electrical saw.
This phenomenon of the right-hand rule is used in a very important application that we all use in our daily life, which is the motor.
The basic operation for how a motor works is bending a wire into a loop shape and running a current through it and embedding it into a magnetic field. Using the right-hand rule that we know, we can see that on the C to D segment of the wire, there will be an upwards force, and the AB side, there will be a downward force. But they both provide torque, which is acting in the same direction, so the frame rotates clockwise.
When the CD segment gets on the right side of the motor and AB gets to the left, the forces will continue to be in the same direction, and this will have the effect to move the frame backwards, and we don't want that. Therefore, we must reverse the direction of or stop the current. To reverse the direction, a commutator is used. In our motor, we use the method of stopping the current, and we will discuss that in more detail later.
There are two types of currents: AC, alternating current, and DC, direct current.
An AC motor alternates currents because the polarity of the electrical source is constantly switching.
DC is a direct current. The motor that we built is a DC motor because the polarity, plus and minus, in the battery is fixed.
To understand why there is a force acting on a current carrying wire and magnetic field, we can remind ourselves about Ampere's law.
What does Ampere's law say?
It says that a current carrying wire creates a magnetic field around it.
Now we finally get to talk about our motor.
We will first talk about how we actually built the motor. What a process.
The yellow wire is wider, meaning that there is less resistance, which produces more current, resulting in heat.
In our design, we have two magnets, 9.5 centimeters away from each other. We place a separator between the magnets so that the magnets would not stick together, but that the two magnets will create a strong enough force.
We started with a 9-volt battery, but later on added more batteries to increase the current in the circuit, which also increases the force.
We only expose a certain part of the wire. The part that is exposed, the current flows as a result of the rotation of the forces. The part of the wire that is not exposed moves from inertia.
Our switch is the circuit breaker, which protects the electrical circuit from damage caused by excess current from an overload or a short circuit.
The circuit that we built is a series circuit. In the series circuit, The current through each load is the same and the total voltage across the circuit is the sum of the voltages across each load.
Here we see a closed circuit once I turn the circuit breaker down, but for now we'll leave that up. And we see where electric current flows from the positive terminal of the battery through the wire, goes around the loop, and returns to the negative terminal of the battery. And we also see that this side of the magnet is the north pole of the magnet, and the magnetic field B is pointed from the north pole of the magnet to the south pole of the magnet, right over here. So we can use the right-hand rule to find the direction of the force. First, let's examine the forces acting on this loop. First, I'll start on the left side right over here. On this side, the current flows in this direction, and B is in this direction. And B is in this direction, so it will be like this. So we see that the force is acting downwards. And on the right side of the loop, the current is flowing this way towards me, and the magnetic field is still facing this way. So it goes like this. So the force is acting upwards. So these forces are acting together as torques to rotate the loop in the direction that we see. So we see that the forces are turning this way.
As a home project, designing and building a commutator is not practical. So we used a different method where we stop the current for half of the cycle so the frame does not oscillate.
The way to stop this current for half cycle is to remove the insulation on only one side of the electric wire, where it touches the terminals.
When the loop completes a half cycle, like this, the current stops flowing because the insulated part of the wire, the red part, is now in touch with the terminals, these things here. And therefore, there are no forces acting in the opposite direction of the loops. And the loops continues to rotate in the second half of the cycle due to inertia. When it comes back to its original position, right here, the original current resumes and the forces are acting again, as I discussed before, to give it another push and the cycle continues.
After we introduce the basic operation of the motor, now we will talk about the factors that affect the performance of the motor.
There are a couple of factors that determine the speed of the motor.
The angular speed of the motor is directly proportional to the magnitude of the torque on the frame. The magnitude of the torque is directly proportional to the magnitude of the force acting on the frame's segment.
The force's magnitude will be directly proportional to four variables: the magnitude of the electric current through the wire, the number of loops of the wire, the length of the wire perpendicular to the field, and the magnetic field strength.
A simple formula to represent that relationship is one where all the variables are multiplied together. Because we're not sure that this product will give us the exact numerical value of the speed, we need to add a multiplying constant. Even if one of the variables increases, the speed will increase as well. And that was our virtual Physics Expo 2020!
Stay safe and healthy!
See you next year, online or in person.
Yay!